Good morning, my name is Petrides, and I will present our work with Professor Pedro Trangoso, titled Heterogeneous and NUMA-aware scheduling for many core architectures. First, the outline of my presentation. I will start with the motivation of our work, then I will present the proposed scheduling policy, followed by the experimental results, and I will finish my presentation with the conclusions of our work. We see multiple architectures expanding over the year in terms of cores. We started with a couple of cores and then we expand to tens and hundreds of cores per chip. In our work, we focus on the Intel SCC many-core architecture, which is a cluster many-core architecture consisted by 48 cores in the chip. More specifically, we want to examine how many-core architectures and cluster many-core architecture can influence application performance and how we can address these issues. The three factors of influencing application performance that I want to study is first the distance of a core to the memory controller. As you can see in the left figure, as the further the core is, the larger the distance is to access the memory controller. Also, the second factor that we want to study is how resources of different core frequency can influence application performance. In the figure on the right, we show our architecture and how cores are set to core frequencies. Different cores of different frequencies can influence application performance. Finally, we want to study how memory controller access contention influences applications, and as the number of concurrent executing applications, this factor, how much is influencing the most applications. In the figure on the left, we can see that the width of the figures shows that as the number of concurrent applications executed on the chip, these access contentions increases. Therefore, it results in a higher influence to the application. We have executed different applications from the SPEC and the NAS benchmark suites in the Intel SCC in order to verify our assumptions. The first figure on the left, we show how the core to the memory controller distance affects applications execution. We have executed applications for different core to memory controller distances, and we have observed that for memory-bound applications, this influence becomes higher and higher, in contrast to compute-bound applications where this influence is very limited. The second factor, the core frequency of the resources, we have executed the same applications on the Intel SCC with three different core frequencies, the 266 MHz, which is the lowest available core frequency on the Intel SCC, and the 800 MHz, which is the highest stable core frequency. You can see that for compute-bound applications, this factor is dominant in contrast to memory-bound applications where this factor is very limited. Finally, in order to study how multiple concurrent applications can influence application performance, we have executed a number of different concurrent instances executing within a cluster. We have seen that as the number of concurrent instances increases, this effect becomes more serious in compute-bound applications, whereas in memory-bound applications, whereas on compute-bound applications, this factor is very limited. So in order to quantify our findings and to express these impact factors on application performance, we have seen that these factors have a linear weight on their application's execution. Therefore, we have expressed this factor in linear functions by monitoring application execution and gathering their RPC matrices. For the distance factor, we have collected this IPC over the distance, and for the frequency factor, we have collected these IPC matrices over the frequency of the core. In order to apply these functions and to have our characterization of the application, we needed discrete couple of cores. That means we needed cores where one of the factor varies, whereas the other remains stable. The first step that our scheduling policy applies is that it takes two cores with same core frequency but different core to memory controller distance. It monitors the application execution to the two cores and determines factor A, which is the distance factor. On the second step, the same application executes on two different cores, whereas the distance of a core to the memory controller is stable and the core frequency varies. With this technique, we can determine factor B, which is the core frequency factor. Having the factors A and B of the executed applications, we can determine which factor is dominant to the application's execution. And by this, we can construct the distance Q and the frequency Q, A and B respectively. An application can exist only in one Q based on its influence to each factor. This is a higher level architecture of our proposed scheduling policy. Each factor has the monitoring mechanism where it collects their IPCs and the state of the core, if it's idle, if it's busy. And all these metrics are gathered to the scheduling policy. We have the application metadata, which are the IPCs. We have the system resources data, which is the core distance, the core frequency, and the state of the core, if it is busy or idle. And the two queues, the A and B queues, which are used in order to define where an application should be placed. Then our assignment policy takes place and relocates applications to the resources. An example of our placement scheduling, we have the different clusters of the chip, each one constituted by 12 cores, with the distance of each core, and the higher the distance is, the higher the frequency is, we set higher frequency to the resources. When our scheduling takes place, we first serve the A queue, that means the distance queue, and we place application closer to the memory controllers. This policy takes in a round-robin way, and all the applications belonging to the A queue are placed to the respective resources. When A queue is empty, then we proceed with B queue, and applications belonging to that queue are placed within the clusters. With this heuristic algorithm, we first serve applications that need to be closer to the memory controller, and then we place applications further, but with higher core frequency as A queue is empty. In addition, we can balance the cumulative off-chip bandwidth of applications, and we have a very good ratio of off-chip memory requests between the clusters. Our experimental setup, we use the Intel SCC main core architecture with 48P54C low power cores. There are 4 memory controllers per 12 chips, per 12 cores, and each core was executing the Linux kernel. We use applications from the SPEC and the NAS benchmark suites, and of different characteristics. We have used compute-bound, medium memory-bound, and higher memory-bound applications in order to examine how mixture of applications can behave with our proposed scheduling algorithm. Because Intel SCC is a cluster memory core architecture, in order to reallocate an application from one resource to another, we needed to use a checkpoint resuming technique, which added an overall overhead of less than 1% to the whole execution of the applications. In addition, we have evaluated our scheduling policy with a number of random static agnostic placement policy scenarios. In our first scenario, we have used one compute-bound and one medium memory-bound application, and on the figure on the left, we show an initial random placement of the applications to the cluster. I have to mention that the memory controllers are on the edges of this grid. Therefore, memory-bound applications should be placed in the edges, and compute-bound applications should be placed on cores with higher core frequency. This is where our scheduling policy converges. That means that it places cores to the compute-bound application to cores with high frequency, tries to address the characteristics and the demands of the memory-bound applications by placing them on the edge and balancing the off-chip cumulative bandwidth. For this scenario, we have observed an overall performance improvement for compute-bound applications of around 27%, and for the medium memory-bound applications of around 4%. In addition, from our results, we can see that the migration time of each application is very limited to their core execution. Also, we can see that applications, the compute power application has a limited time spent on lower core frequencies, in contrast to memory bound applications, where the majority of execution time is on the lower core frequencies and on the edges of the grid. Our second scenario, we wanted to study the same algorithm using one compute bound application and using a high memory bound application, more demanding than the previous one. This is another random initial state example of placement of applications to the resources, and this is how our application, our proposed scheduling converges to. Again, for this scenario, we have observed a better overall performance improvement for the high memory bound application, about 50%, and for the compute bound application, around 26%. For this scenario as well, we have seen that the migration overhead is limited, and the time spent for the compute bound applications on low core frequencies is less than the random one, and in contrast to memory bound applications. For our first scenario, we wanted to see how applications are behaving, how our scheduling policy behaves when we have one compute and two memory bound applications. In this scenario, this is an initial state of a random initial state of the placement of applications to the resources, and here is how our proposed scheduler converges. In this scenario, we have observed a limited performance improvement for Sphinx around 1%, for the high memory bound around 10%, and for Povray, which is a compute bound application, to around 34%. Again, for this scenario, the migration overheads are very limited to the total execution time of our scheduling policy, and the limited we have to show that Sphinx, which is a medium bound application, is placed a little bit further than the high memory bound application, which is with lip bundle. Therefore, it balances well both the off-chip memory bandwidth, but at the same time, it serves good the demands of applications in terms of core to memory controller distance. For our fourth scenario, we have only memory bound applications executing, and this is again an initial random placement of the applications to the resources. And this is how our proposed scheduler converges to. Again, the high memory demanding applications are placed closer to the memory controllers, whereas the lower memory demanding applications are placed further from the core to memory controller distance. This is due to the fact that AQ, which is the distance Q, is sorted by the factor that each application is influenced by. For this scenario, again, Sphinx shows a limited performance improvement of around 1%, and Lip Quantum about 8%. For this scenario as well, the migration overheads are very limited. For our fifth scenario, we have used only compute power application, the Povray, and this is an initial state, but in this scenario, when resources are available to applications, then our scheduler takes place and relocates applications which were misplaced from the beginning. Therefore, applications belonging to lower core frequencies are placed to higher core frequencies. For this scenario, we have observed an overall performance improvement of 80%, and again, migration overheads are very limited to less than 1% of the total execution of the applications. So for the conclusions of our work, we proposed an online heuristic scheduler policy, which tries to satisfy applications' demands and behavior in terms of the available resources and the available architecture. We have implemented in a real architecture, the Intel SCC, and using real workloads from SPEC and NAS benchmark suites. We have observed an overall performance improvement for compute-bound applications of around 36% and for memory-bound applications of around 15%. Thank you.
does your algorithm behave if you have different phases of execution in your program?
It keeps monitoring the application's behavior, and it triggers the scheduling algorithm when it identifies that an application changed its behavior. Therefore, the queues are constructed and remain in the queues for the full execution. And if that occurs, then it reconstructs the queues. Therefore, if an application was limited to the influence of the distance, and now it's influencing the distance more, then that application is moved to the head of the queue, and then that application is rescheduled, is replaced, and it's satisfied at that point.
Anyone else? I was wondering, you kept noting that the live migration overhead was had a very small overhead. Were there cases in which you noticed that there was a significant overhead for the migration? Or is this algorithm, does it have any caveats? Is it not good for anything?
No, it has. It has migration overheads. Yeah. The migration we put here is the time to checkpoint and replace an application to a respective resource. But the overhead we have is to identify where an application should be placed. It's not included the time to decide. So it's the actual execution time of the application to the resources. But we keep the applications executing, and the assignment policy takes place outside of the core to the host PC, which hosts the SCC, and that triggers the migration.
So this time is significant.
It's around 7 to 10% of the application.
I see. Okay, thank you. Okay, thank you.